4 minutes late getting started, sorry. My memory is, I think I'm right on this, we're just going to do a quick slideshow, if I can do anything quickly, on 11.7 and then move on to chapter 12. Is that right? Okay. Now, one thing I do remember from the email that I was reading last night, just aggravated me no end. They've assigned a whole bunch of us to go to some, sounds like really ridiculous set of meetings over at Shelton State, not this coming Monday, but the following Monday. I think that's the 13th or, no, whatever, no, it wouldn't be the 13th. 15th maybe?
16th.
Huh?
16th.
16th. I've got to go back and check that because it seemed like, huh?
The 9th through the 16th.
Yeah. So anyway, I'll have to check and find out for sure, but it's I think utterly ridiculous. Here we have classes during the week. Friday is usually a meeting type day. Why don't they have this meeting on Friday? Minimize the class disruption, but I think the administrators like to play golf on Friday. I didn't say that, did I? Out loud. Okay. So anyway, we may be missing not this coming Monday, but the following Monday from class. Okay. Okay. Let's pick up and go from there. So let's look at vectors in geometry of space, which we've been on for a while. 11.7 is cylindrical and spherical coordinates. We're just going to go over these briefly. But before we do, any questions from anything else we've covered so far? Okay. All right. Cylindrical and spherical coordinates. We'll use cylindrical coordinates to represent surfaces in space and spherical coordinates to represent surfaces in space. We may not do all that. We'll just introduce you to them anyway. So let's look at cylindrical coordinates. The cylindrical coordinate system is an extension of the polar coordinate system that you use in a plane. You're extending this to three-space, okay, three-dimensional space. Now, this is the Cartesian coordinate system, x, y. Those are your variables. In polar coordinates, you have r and theta as your variables. R being the radius and theta being an angle, okay? And that radius and angle will specify any point in space. Now, some of those can be the same. One advantage for Cartesian coordinates, you give me an XYZ or XY coordinates, that's one and only one point, okay? And there's only one XY coordinate for that point. But in polar coordinates, with this R and this theta, that's the same as that R and that theta. You know, so you have multiple ways to do, and you really run into the same thing in cylindrical coordinates too. So cylindrical coordinates, when in free space on Cartesian coordinate system, you just have the z-axis coming out of the middle here. Actually, usually lay this down and then have the z-axis do it. In cylindrical coordinates, what you have is concentric circles representing various radii. Now you just bring those out. So it's really the same type deal as you do for Cartesian coordinates. In cylindrical coordinate system, the point P in space is represented by the ordered triplet, R, theta, and then Z. R theta tells you where you are on the R theta plane, and then how high you go, Z. It's just like XY plane, then how high you go, Z. Same type thing. R theta is the polar representation of the projection of P onto the XY plane, or the R theta plane, and Z is then the directed distance from that R theta to P. So it's just, Z is just how high you are above the R theta plane, just like it is in the Cartesian coordinate system. Okay? Now, to convert from rectangular to cylindrical coordinates, or vice versa, use the conversion guidelines for polar coordinates listed below, illustrated in the figure over here. Okay. Cylindrical to rectangular, x is still r cosine theta, just like it's always been. Y is equal to r sine theta, and z is the same as z. It's the same z. Okay? When you go from rectangular to cylindrical, r squared is still x squared plus y squared, and tangent theta is still y over x. And z is equal to z. Okay? It's the same thing. So you're just taking your polar coordinates that you have in the xy plane or the r theta plane, and then going up z or down z, but z is the same. Make sense? Here, perhaps you might see this a little better. That's your r, and that's your theta. The x is equal to r times the cosine, the adjacent side of theta, whereas y is r times the opposite side of theta. This is your y. So that's the sine theta, r sine theta. And z is just z. Go up or down from that. And tangent of theta, y over x is tangent theta. And x squared plus y squared is equal to r squared. It's just same old, same old. Now, the point 0, 0, 0 is called the pole rather than the origin in cylindrical coordinates, because the representation of a point in the polar coordinate system is not unique. That's what I was trying to say before. It follows that the representation in the cylindrical coordinate system is also not unique. You can have a variety of representations. They're all going to be related to each other. So it's not just random. They all will be related by certain ways. So you can do this without too much problem at all. If you're trying to convert to a rectangular coordinate system, your x would be what?
4 cosine.
4 times the cosine of pi, 5 pi 6. So you can figure out what that is. 5 pi 6 would be almost over here to 6 pi 6, or pi. You're just pi 6 short. And your x is negative over here, so that would be 4 times, I think a negative 2, isn't it? Because if this is your radius, that's your hypotenuse, and the no, it's root 3 over 3. Yeah. The cosine of pi 6 is root 3 over 2. Yeah. So it would be 2 root 3. Okay? Would be your x coordinate. Your y coordinate would be the one that's positive, and that would just be 2. And then your z coordinate is 3. I'm doing it in my head without working it out, so I hope I'm getting it right. Yeah, x coordinate is negative 2 root 3. Y coordinate is 2. And the z coordinate is just the z, 3. So negative 2 root 3, 2, 3. Okay. And again, you're not going to be tested on this, so don't waste too much, but just in case you ever need them, here they are. Okay, you've seen them, and they're not that hard to get to. So in rectangular coordinates, the point x, y, z is negative 2 root 3, 2, 3, and here is represented by your r is 4. Okay, so that length is 4 here. The angle theta is 5 pi 6, it's just short of pi, short by pi 6. And the cosine of that is root 3 over 2, so that's where that came from. sine is just 1/2. So negative for the x, because you're in the negative x direction, positive on y, so that would be 2, and then you're up there at 3. So that would be negative 2√3, which is somewhere back in here, okay, short of 4. 2 this way, and 3 All right. Cylindrical coordinates are especially convenient for representing cylindrical surfaces and surfaces of revolution with the z-axis as the axis of symmetry. So a cylinder certainly works really well in a cylindrical coordinate system. Here is just x squared plus y squared is equal to 9. This would just be r is equal to 3. Doesn't matter what the theta is, doesn't matter what the z is. Okay. Here is a, what shape would you call this? Or they tell you here. A paraboloid, okay. And this is a circular paraboloid, by the way. This is your r squared. X squared plus y squared is r squared. So the r would be the square root of 4, which is 2, times the square root of z. So there you have it. And of course, the z can't be negative here because this is positive, that has to be positive, so that makes sense there. This is your cone. X squared plus y squared is equal to z squared. 0, 0, 0 is the place that goes to the origin here. And then this is just simply r is equal to z. Okay? Because this is r squared. So r is equal to z. I would say a little better than that is r is equal to plus or minus z. But it's okay, r is equal to z as well. This is your hyperboloid of one sheet. And again, this is your r squared. So r squared minus z squared is equal to 1. So r squared is equal to z squared plus 1. Because the z's are the same. You don't worry about them at all. So some of these are very easily represented because if the z-axis is your axis of symmetry, it just works out perfectly to use cylindrical coordinates. Now, vertical planes containing the z-axis and horizontal planes also have simple cylindrical coordinates shown here. This would just be theta is equal to c. Any vertical plane that contains the z-axis, you just define it by whatever the angle that is from the x-axis. That's simple. Theta equals c. Horizontal planes are also very simple because it's just z is equal to whatever the constant is. As long as they're horizontal. You get a tilt in them, you got some problems. Vertical planes not centered on the z-axis, that gets a little more complicated. But these are really, really easy. Okay? Now let's look at spherical coordinates. These are a bit weirder, okay, to put it mildly. Sorry. In the spherical coordinate system, each point is represented by an ordered triplet, 3 space, so you have to have 3 coordinates. The first coordinate is a distance, and it's the only distance you have. In rectangular coordinates, all 3 coordinates are distances. In the cylindrical coordinates, 2, the r and the z are both distances. Here, only one, the first coordinate, is a distance. The second and third coordinates are angles, whereas in the cylindrical coordinate system, just the second coordinate is an angle. This system is similar to latitude, longitude system used to identify points on the surface of the Earth. There, points on the surface of the Earth are always the same distance from the center, okay? So that makes that pretty easy, and then you just give, because that's always going to be the radius of the Earth, and then the latitude will be 1 and longitude will be another. It's just reverse. It's longitude, then latitude. So, for example, the point, point on the surface of the Earth whose latitude is 40 degrees north. Here's the equator here, I assume. There's 40 degrees north of the equator, and whose longitude is 80 degrees west of the prime meridian. That happens to run through Greenwich, England, which is where the Royal Naval Observatory was, so they chose that as the prime meridian. England was queen of the seas, and they used this more than anyone, so that's where they decided the prime meridian. 80 degrees west, 20, 40, 60, 80 degrees west, somewhere up, maybe upstate New York, Pennsylvania, somewhere in there. It looks like about where you are there. Assuming the Earth is spherical, which is not quite, but it's pretty close, and has a radius of about 4,000 miles, then you would label this point radius 4,000, and then you give the sort of the azimuth angle next, and you go, since you're going clockwise from the prime meridian looking down, that's a negative. Counterclockwise would be positive, so it would be a negative 80, that's west, and then 50. They cut it backwards. This supposed to be a 40 here. Oh, no, sorry. Spherical coordinates measure down from the North Pole. They do not measure. Why didn't they show us that first? And then that would have made more sense. You measure down from the vertical, and so that gave you 90 minus 40 is 50. So that would be what you use there. So here's the spherical coordinate system. In the spherical coordinate system, the point P in space is represented by an ordered triplet. Now they don't call it R anymore. It's rho. And that is a three-dimensional radius, a spherical radius. Theta is similar to the theta that we use in polar and cylindrical movement. And then phi is the angle down from the North Pole, basically. Rho is a lowercase Greek letter rho. Phi is a lowercase Greek letter phi. Okay, and that, of course, is lowercase theta. I'm sorry, I got a frog in my throat. Rho is the distance between P, the point that you're dealing with, your origin, you might say. No, I'm sorry, the point that you're looking at and the origin. So rho is always greater than or equal to 0. Rho is 0 only out at the origin. Okay? Everywhere else is positive. Theta is the same angle used in cylindrical coordinates for r greater than 0. Why they say that, if you have your r being negative, then you sort of messes with the theta. But for all positive r's, you do that. See, in cylindrical coordinates, they do allow r to be negative, which is rather strange, but they do. You don't allow the rho to be negative in spherical coordinates. And phi is the angle between the positive z-axis and the line segment 0p. That's the line going from the origin to the point P of question. And this is always between 0 and pi. Pi takes you all the way down to the South Pole, and you don't ever go any beyond that. So you don't have negative phis. You could have a negative theta, but phis are always positive and rhos are always positive. Notice that the first and third coordinates are non-negative. Okay. I say always positive. They can be 0. So the relationship between rectangular and spherical coordinates is illustrated in this figure, and it's a rather strange relationship. So this is one I just want you to see, to recognize, so if you ever need it, you'll know where to look to go back and find it. To convert from one system to the other, use the conversion guidelines listed below. So, spherical to rectangular. Okay? Your x-coordinate, what you do is go from the rho to the r. Okay? And rho comes out in space like this, and here's your phi measured like this. So your r down here, this makes it look like r is greater than rho. It never is. It could be equal to, but never greater than. It's just that this is coming out, and this is just trying to draw a three-dimensional object on a two-dimensional board here. The cosine of this angle, the sine of this angle is the opposite side, okay? And that's what you have here. So this would be, to get to the r here, it's rho sine phi. There's your r is equal to rho sine phi. Now, and r, of course, is the same as x squared plus y squared, okay? So that gets you to your rho, to the r, okay? And then to get the x out of it is the r times the cosine. The x is the adjacent side, cosine of theta. So the x coordinate here is rho times the sine of phi, that gives you your r, times the cosine of theta, that gives you your x. Okay? The y, you have to get to the r again, so it's still rho sine phi, but now it's sine, because the y value here is the same as that, is the sine of theta. So rho sine phi sine theta. And then the z is just simply rho, that's the length here, times the cosine. That's the adjacent side of this angle, phi. So it's rho phi sine, cosine phi. All right, going the other way. Your rho squared is just simply x squared plus y squared plus z squared. That is your the distance here. Keep wanting to say on a sphere, and yeah, it would be on the sphere of radius rho. Okay, because all these coefficients are 1. X squared plus y squared plus z squared. And your phi, your theta is just like it was before. It's the tangent of theta is y over x, just like before. Okay, because on the xy plane, it's just like the theta on the polar coordinates or cylindrical coordinates. Now your phi, oh man, it is. This angle phi is the arc cosine of the z over the rho. And the rho is the square root of x squared plus y squared plus z squared. And so if you want to end from rectangular to spherical, you don't want to say rho here, you say square root of x squared plus y squared plus z squared. Now, I can't ever remember actually using this. I'm sure there are places where you can use it, but these are just the formulas you use if and when you ever need to, which you probably hope will not be very common. Okay. Any questions? Ready to move on? All right, to change coordinates between cylindrical and spherical, we would want to do that, but you should be able to. Wish they still had the picture here. If you go back here, we already said this r was equal to rho times the sine of phi, right? So, why do they square everything? let's say R is equal to rho cosine phi. Seems like that would make more sense. The theta is the same, and Z is equal to rho cosine phi. I haven't figured out why they did that yet. Okay? So much simpler to say, I guess this is it. Because this rho could be plus or minus, R can be plus or minus. Rho is always positive. Since phi is always between 0 and pi, sine phi is always positive. So if you just said R is equal to rho sine phi, then that R can never be negative. And since it can be, if you square everything, it allows that. Okay. And then going the other way, R squared plus Z squared is exactly rho squared, so that's going to be rho would be the square root of R squared plus Z squared. Theta is equal to theta, that stays the same, and the phi is the arc cosine. It's very similar to it in the other because remember R squared is x squared plus y squared, so this is Z over the square root of R squared plus Z squared. So those are fairly straightforward, but nothing completely obvious. Okay. I hadn't thought of that you do need to account for a negative R. Very seldom in spherical or, in cylindrical or polar coordinates will you use negative R's, but it's okay to. So they have to account for that here. Need it any longer? Okay. Some of the things that will work really well in spherical coordinates is, of course, spheres, okay? They work incredibly well in spherical coordinates because rho is equal to some constant. That makes the sphere, okay? A vertical half plane, can't do the whole plane now, but the half plane is theta is equal to C, okay? Just like the whole plane was in cylindrical coordinates, as long as it passes through the z-axis. That would be it. And then cones work quite well, or at least half cones do, because your phi is now equal to some constant. And that makes a cone all the way around. Half a cone. As long as the C is between 0 and pi halves. If you're pi halves, you're on the XY plane. If it's less, then you've got half of the cone. All right. Those are some of the shapes. This is example 5. Find an equation in spherical coordinates for the surface represented by each of the rectangular system. Okay. Spherical coordinates, okay. That's a great little exercise. I'll just show you how they did it, just to keep from spending too much time. Of course, this is going to be R squared. This one would be fairly easy. R squared, well, let's just show how they did. Using spherical to rectangular equations, which are fairly complex, but they are fairly straightforward. Substitute the rectangular, and substitute in the rectangular equation as shown. Okay, so basically, you square this, you square that, and you square that, and then just plug these things in, and it looks awful. Okay, until you realize you have a square of rho squared in every term, and you can divide those out. Okay, and that will make things a little simpler to just, there's the original formula. plugging all those squares in, you can divide out the row squares, and okay, and the sine squared phis, you can divide those out as well. And this, of course, gives you 1. That still works in any coordinate system, so that's still 1. And so you basically have sine squared phi is equal to cosine squared phi. Looks like that, doesn't it? Or sine squared phi over cosine squared phi is equal to 1. Okay, as long as the row is greater than 0, which of course it always is. Okay, so that's tangent squared is equal to 1. Pretty simple, coming down to that. Okay, our tangent is equal to plus or minus 1, which means phi is the angle pi fourths or 3/4 pi, or pi fourths or 3/4 pi. So that was which? That was your cone. So it comes down to the specifics they gave you that. The equation 3/4 pi is the upper half cone. 1/4 pi is the upper half cone. 3/4 pi is the lower half cone. All right, now this one, like I said, the row square is pretty obvious. So you have, and z was rho cosine phi. So that gave you rho squared where your x plus y squared, and then minus 4 times z, and z being rho cosine phi, equal to 0. Factor out a rho, and you have rho times rho minus 4 cosine phi equals 0. So either rho is equal to 0, which isn't very interesting, or rho is equal to 4 cosine phi. Okay? So we'll discard the possibility of rho is 0. You wouldn't have, so you would have rho is equal to 4 cosine phi. Which one was that again? That's the sphere. Okay. This one's not centered at the origin. Okay. So that's why you have that rho is equal to 4 times the cosine of phi. Note that the solution set for that equation includes a point for which rho is equal to 0, so nothing is lost by discarding that factor rho. Sphere shown represented here as rho is equal to 4 cosine phi, and there it is there. Your center is located up there at plus 2. Whoa, and that's all. Anyone need any of that any longer? Okay. That one. Okay. There are some problems just set up far better if you start with spherical coordinates. Others, if you start with cylindrical. But most work pretty well in rectangular too. But if you start getting lots of cross terms and things like this, sometimes going to one of the other systems will greatly simplify things. Okay? All right. Everybody? Okay. All right, then let's move on. Okay. So that does it for 11. All you're responsible for is 11.6. I did want to show you 11.7, and y'all wanted to see, I think, yeah, some of 11.5. So we've been through that. Now let's move to 12. And Chapter 12 is vector valued functions. Now, if that almost sounds familiar, you might be confusing it with vectors and the geometry of space. That was chapter 11, which we just did. Or, if you remember what we talked about earlier, we're going to do chapter 15, which is vector analysis, which is not quite the same as vector valued functions. Okay? So let's look at vector valued functions, and 12.1 is also vector valued functions. Sort of an introduction to it, and then we'll be doing various things with it. So what we'll do here in this one, our objectives are to analyze and sketch a space curve given by a vector value function. We'll extend the concepts of limits and continuity to vector value functions. That sounds like just such an exciting thing to do, doesn't it? Since those are some of our favorite things in all the world. So let's look at space curves and vector valued functions. Remember, a plane curve on the plane here is defined as a set of ordered pairs, but now the elements of the ordered pairs are not numbers, but functions. F of t is your x, g of t is your y. Together with the defining parametric equations, that x is equal to some f of t, where that's your defining equation, and y is equal to g of t, where that's your defining equation, and f and g are continuous functions of t on the interval I. Now this interval I is the interval containing t, not x and y, but t, or not just x or anything. Your independent variable here is t, not x. Okay, x is an intermediate function, variable, not a independent variable. This definition can be extended naturally to three-dimensional space, and frankly can be extended further, but we can't see any further than that. The space curve C. Okay, now this is kind of a new concept. Rather than talking about the graph, we talk about a space curve. It's a set of all ordered triplets, f of t, y of t, h of t, f of t, g of t, h of t, together with the defining parametric equations. X is equal to f of t, y is equal to g of t, and z is equal to h of t. Where f, g, and h are now all continuous functions of the independent variable t, and that t belongs in this interval I. Now, a lot of times this t is going to be time, but it doesn't have to be. It's just a parameter. Just a parameter. So don't get to thinking it's always talking about time. Because usually time is not negative. T could be negative. So don't kind of restrict it. A new type of function called a vector valued function is introduced, which is what the name of the chapter in this and the section is. This type of function maps real numbers to vectors. So given a real number t, you now get a vector r of t. Okay? So if r of t would then be your f of ti, okay, where f of t is your x, and g of t j, where g of t is the y. That's in a plane. In space, r of t would be f of ti plus g of tj plus h of t k. okay, corresponding to some point in space, which is your unit vector in I direction is good. So this sort of makes perfect sense, I hope. These both are vector value functions where the component functions f, g, and h are real valued functions. They're not vectors, real valued functions of the parameter t. And the vector value functions are sometimes denoted as this. The r of t, this one up here, would be angle bracket f of t comma g of t angle bracket. That's in a plane in space f of t angle bracket f of t comma g of t comma h of t, where this is your x, y, z. Okay. Just like we did before, only now we've got functions in there, real valued functions rather than just numbers, okay, or variables. All right. Technically, a curve in the plane or in space consists of a collection of the points and the defining parametric equations. Two different curves can have the same graph because you can just define things differently. For instance, each of these curves, r of t is equal to sine ti plus cosine tj. Okay? That will be a circle. Okay? This will be sine of t squared I cosine of t squared j. Both of these are unit circles as a graph, but the equations do not represent the same curve because the circle is traced in different ways on the graph. Okay? In this way, if t is starting at 0, then your x would be 1 and your y would be 0, and then you'd go this way and this way and this way and that way. Here, when t is equal to 0, you start at 1, okay, and 1, 0, okay, and then when t increases, the curve also increases, but one thing you won't see is the t going, even if t goes negative, this is still positive, okay? And it just acts differently, okay? You can play around with it and see its effect of squaring the parameter t. Yes?
Okay, in the first one, sine t cosine t. Okay?
This one.
Yes.
Yeah.
How do I know whether I'm going to go negative or positive?
Okay.
Clockwise or...
Okay.
How do I know?
Okay.
It wasn't making a difference, I think it's not.
Right. Okay. You start with t equals 0, and as t increases, then your sine is increasing. Okay. Wait, I said it backwards, I think. I wasn't paying attention. Usually I think that this is cosine. Sorry. This one starts with, when t is equal to 0, this is 0. So 0 on I and 1 on j. So you're starting up here. Here's your first point. And then as t increases, sine goes more positive. So that is going clockwise. And cosine is going more negative. So this is going clockwise like this. So you're absolutely right. I was thinking cosine t I plus sine tj. But this is going like this. Okay? It's going clockwise because you just let the t increase. Pick a starting point, like t equals 0. That would be 0i, 1j. Okay? And then as t increases from 0, sine goes positive. Cosine is still positive, but it's now it's decreasing. So your y is going down, your x is going up. Okay? And you go around the circle like that. On this one, you're starting at 0 again, 0, 1. and then when t is increasing, it starts off sort of slow. If t is a very small increase, then t squared is going to be even smaller. So it's starting really slowly coming around. But then when t picks up and gets greater than 1, then the t squared is increasing. So basically that one's going at a faster speed is what it is. It starts slow. This goes sort of uniformly. Not that we're talking speed here, but you know, that seems to be what it is. That's just a bizarre one there because t can never, well, t could be negative. T can be negative here, but your arguments stay positive always. And I'm trying to think how you ever then get it back around here. Well, that's because when, the sign goes negative when you pass pi. So that would be when you pass square root of pi there. Then your sign goes negative. So, yeah, it's the curve circle is just drawn in a different manner on the two. We're going to see some of these later. I don't particularly want to draw them myself because they're sort of a pain in the neck to draw. All right. Be sure that you see the distinction between a vector value function R and the real value functions F, G, and H. Somehow that doesn't seem to be a big deal for me because R contains all of those, so you can't be confusing them. Okay? All are functions of the real value t. The R of t is a vector, that's why it's bolded like this, and these are just numbers, scalar values, okay, for any particular value of t. The real value functions are sometimes called scalar functions. This distinguishes them from vector value functions. So I don't want to say scalar valued function, but usually you just don't, you leave that out. Okay. Vector valued functions serve dual roles in the representation of curves. Now this gets to be a little confusing because the things sound so similar. By letting the parameter t represent time, that's only if it's the time, you can use a vector value function to represent motion along a curve. Okay? But even if it doesn't represent time, you still indicate motion by which you put an arrow on the curve showing an increase of t goes in this direction, whether the t represents time or something else. You still put the arrow on it. Okay, you can use vector value function to represent motion along a curve. Or in the more general case, you can use a vector value function to trace the graph of a curve. So you can either let it be the curve or represent motion along the curve, or you can let it trace the curve. So what I was describing before, pick a t, give it a point here, point there, and you trace a curve out here. That's what this is talking about. This one's talking about at different values of time, where are you on the curve? That indicates motion along the curve. And really, there doesn't seem to be a big difference between motion along the curve and tracing the curve. I mean, you're almost doing the same thing. But later we'll then talk about a velocity and acceleration using this concept, and that wouldn't necessarily make sense if it's just tracing a curve. How fast it traces it doesn't matter. You're just tracing a curve. Okay. In either case, the terminal point of the vector, R of t, coincides with the point xy or xyz, the terminal point, okay, on the curve given by the parametric equations. So this is in a plane, so this R of t is two-component vector. At T0 you're here, at T1 you're here, and at T2 you're there. This is tracing out the curve C at these various times and connect the dots. Okay? In 3 space, here's the problem. You can't tell where it's going except they've drawn some things in here that help. At time t equals 0, you're here. It looks like you're directly above the x-axis. So you have an x component and a z component, but no y component. The y component is 0. At time t equals 0. Well, it doesn't have to be time. At parameter t0. Okay? At parameter t1, I keep on saying time t1, parameter t1, you've moved over here. It looks like the x has almost stayed about the same, but the y has increased. The z certainly has increased as well. Okay? And then at some value when t is equal to t2, your curve that this is tracing out, because you're not talking about time here necessarily, so you're not talking about motion, but you're going to over here. Now your x value has gone to 0, your y value is taken over, whereas here you didn't have a y value, and your z looks like it's gone down some from this one and about the same way it started here. So this curve is going up and coming back down like that. Okay?
Wait a minute, say it again. You going like this and then over there?
Yeah, that's what it looks like. It looks like you started here, you went up a little ways, and then you came around down there. So this, but it doesn't show there's a corner there, so it was a gradual thing. But I may be wrong on saying, but it looks like to me those are awfully close. It may have gone out a little in x, not just increased in x, but it increased in y. So it started here and maybe went out a little bit and came back in. It's just hard to see. You can't tell what this is doing in 2 dimensions. In 3 dimensions, well, all you got is a 2-dimensional representation. It could have come out here and happened to just be going back that way. It's really hard to say. Okay. But this is tracing out the curve. If t had represented time, then that's showing motion along the curve. But notice here, and this I think you were asking before, as your t is increasing, you always have your arrow on the curve indicating the direction along that curve. Because this is you're tracing the curve, and you've got to show which trace showed up first, second, third, so the motion is that way. Now, later we'll have curves that close on themselves and do all sorts of weird looking things, and then you really have to keep up with what it's doing, that it's not doing this and this. It can get really confusing. And again, one of the problems is you're trying to draw a 3-dimensional shape on a 2-dimensional board, and it's a really hard thing to do. The arrowhead in the curve indicates the curve's orientation by pointing in the direction of increasing values of t. So if t even started out some negative value, as long as it was increasing, you went that way. Unless stated otherwise, the domain of the vector value function t of r, vector value function r, is considered to be the intersection of the domains of the component functions f, g, and h. Now, what that means, f may have some limitations on it. G may have some limitations. They may be the same or different limitations. H may still have other limitations, or not. It may not. But you have to have the intersection of all those domains. So what if this is your vector value function. R of t is equal to log ti plus square root of 1 minus tj plus tk. Okay? What would be its domain?
Can't be zero.
Can't be zero.
Then on the right.
And it also can't be negative.
Yeah.
Okay, so it only can be positive. Okay.
Okay. Then
And
on
here,
the radical, it can only be 1 or less.
1 or less. It can be 1, and it can be less, but it can't be less than 0. It can't even be 0. So that makes it from open parenthesis 0 to close bracket 1. Because it can be 1. Okay. Welcome to any t. But it can't because of these two limitations. This has a limitation on this end, that has a limitation on that end. That gives you your domain of that and that alone. Okay, for this vector value function R. Very good. That's what we mean by the intersection. They have to be contained by every domain listed. Okay. Whoa. Have we already done example 1? I think they skipped example 1, didn't they? Yep. Okay. Let's go back and us do example 1. Let's find some. Let's do it here. Okay. Most white space we got. We'll do 1 first, then we'll come back and do example 2. Okay. Sketch the plane curve represented by the vector value function R of t. I can't write bold, so I put an arrow over mine. Is equal to 2 cosine t. And when I'm writing something I know to be a unit vector, I put a caret over the top rather than bolding. Rather than an arrow. That indicates that's a unit vector, if I know it is. Minus 3 times sine t j. Okay? In this case, they tell us that t varies from 0 to 2 pi. Okay, that's the vector value function. We're supposed to sketch the plane curve represented by that vector value function. Okay. Probably won't need all those, but because I'm not willing to take and spend the time to figure out what I will need, I'll just draw them in here. We'll expand later if we need to. Okay, we know where we're starting. T is equal to 0. So where would that begin?
Cosine, 2 cosine. That'll be 1.
Okay, cosine 0 is 1. 2 times 1 is 2. So 2i. So we're going to start somewhere perpendicular, perpendicular to that point there. Minus 3 sine t, well, when t is equal to 0, yeah, that's 0. So that is exactly where we start. There is when t is equal to 0. Okay? Guess we're going to have to do some fractional ones here. I kind of regret that. Let's take pi halves. That's usually a good one. So cosine of pi halves is what? Second? 0. So you got a 0i here, and minus 3 times sine of 0 is 1. I mean, not 0. Pi halves is 1. So you got minus 3j. Okay, somehow we got down there. I think it was straightforward. Okay. Then let's do, why not sine of or t equal pi and just see what happens. Oh man, eyes are itching like crazy. Getting congested. I don't know what's going on here. Okay, t equal 3 pi. Let's do pi. Yeah. Cosine of pi is what? So the I component would be a -2 here. And how about the sine? 0. So that's going to be there. And let's go then to that was pi. Let's do 3/2 pi. Cosine of 3/2 pi is yeah. 0. Okay. So 0i and second.
It's -1%.
Okay, so -1 times -3 is +3. All right, it goes up there, and then 2 pi should take us right back to where we were. Now, I believe we can basically conclude from this that everything is fairly smooth in between. They certainly are continuous in between, so they should be smooth. I don't think it does any curly cueing or things like that. So it basically looks like this is going to be an ellipse. All right. That's what it appears to me to be. Okay. And which way is it going? Counterclockwise, right? Because we plotted that one first, second, third, fourth, and back around. So that's an ellipse. Okay. That was, I guess, fairly easily done. Trying to see. Yeah, let's just leave it alone. That's all they ask us to do, so let's not do any more with it. So now, all right, to erase. Okay. This is example 2. Sketch a space curve, okay, represented by the vector value function 4 cosine ti plus 4 sine tj plus tk. All right. That previous one was fairly easy. This individual points are not bad, but boy, getting the connections made. This is your x, your y, and your z. Okay. Sketch the space curve represented by that function. So again, and here they give us a range, 0 to 2 pi. Now the last one closed on itself, so that made a closed structure. This one, I can guarantee you it will not. Okay? We're not going to need it, but if you did need it, your negative z goes down here, your negative y, we might need a negative y, and the negative x, you might need that, but you're not going to need the negative z. Okay. Sketch the space curve represented by the vector value function. R of t is equal to 4 cosine ti plus 4 sine tj plus tk. 0 to 2 pi for t's. So let's start with t equals 0. Where do we begin?
X will be 1.
Okay, just a minute. Say again.
X will be 1.
X, you said? Is that, I just can't
I'm
hear.
sorry, 4. X will be
4, okay. So the first value here will be 4 here. When t is equal to 0, you'll be 4 on x, 0 on y, because sine of 0 is 0, and then 0 on k. So j will be 0 because sine is 0, and k will be 0 because t is 0. Okay, so there's where we begin. All right, let's move to t equal 1/2. What's cosine of 1/2? Pi halves, pi halves. 0. Sine of pi halves is 1. So you go 0 on x, 4 on y. So you've gone to here. Except that now you're pi halves up. And pi halves up is about 1.57, right? So you've gone up about here. So here's where we are. Not there, but there. Let me get my pen back. Okay. All right. Need my pen back. Goodness gracious. I don't know. It's not that much heat coming off here. For some reason, something's drying my eyes out like crazy. Let's move on to pi, t equal pi. Cosine of pi is? Okay, so you'll be back here. X will be -4. Y will be 0. But your K will be pi, okay, which is 3.14. So here would be 1, 2, 3, 4, where you would be on the XY plane, but you go up 1, 2, 3 spaces from that, 1, 2, 3, and a little bit. Okay, so you've gone from here around to there, and then you come back in about there. I'm probably not leaving enough room for it to make sense. Okay, probably still doesn't make a lot of sense, but some. Okay, that's pi. Let's now do t is equal to 3 pi over 2. Okay. What is the cosine of 3/2 pi? 0. So the x is 0. What's the sine of 3 pi over 2? -1. So you got 4 times that, so it's -4. Okay. All right, and your z would then be, oh boy, what are we at? 3/2 pi? That'd be about 9/2, about 4.5, a little bit more than that. So you were over here, I believe is where you were, and you go up 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so somewhere about there. Okay, so this one goes up here to there, And let's now do t is equal to 2 pi. Okay, I can't read my own writing there. 2 pi. Goodness gracious, I'm feeling lousy. What's cosine at 2 pi?
1.
Yeah, okay, you're 4 again. And you're right over this one again. But now we're up here at 2 pi is about 6. 1, 2, 3, 4, 5, 6. Okay? So you go out and you make a really be steep curve. Now this representation really stinks. 1, 2, 3, 4, 5. Because you can't really tell what's going on here. And I can't draw it either. You see your x-axis is sliding down. I think I got this one too tall here. No, I didn't get it tall enough. Anyway, it's going around and around, and when it's coming toward you, it looks like it's coming down, but it really isn't. It's still going up. It's just that it's coming toward you, and your plane is tilted this way. So that's what you got. Basically, what you got here is a helix. Okay? Picture a tin can. This isn't a tin can. It's not a tin, and it's not a can. But if you went around like this and kept going around and around and around that shape, that's what you are doing here. And that's your thing. This part here tracks on the xy plane as a circle of radius 4. Okay? This has it climbing at the rate 0 to 2 pi. Going from 0 here to 1.5 to 3 to 4.5 to 6. So I think I got this one way too high over here. I don't know how I got that high. Yeah, that should have been down here somewhere. I think I was chasing a stray dot rather than a dot I should have had. Okay. Okay, let me see if I, oops. Okay. This one over here was here. We should have gone up 4.5 to here. So, and then this one curves around to there. And you keep going up. So you're going around and around and around. Okay. I don't draw these things well at all. So why was I even messing with that? Let's just see how theirs looks. Okay? From the first two parametric equations, x equal 4 cosine t and y is equal to 4 sine t, you can obtain x squared plus y squared is equal to 16, which is a circle of radius 4. Means the curve lies on a right circular cylinder of radius 4, centered on the z-axis, and to locate the curve on that cylinder, you use the third parameter to climb slowly at the rate of 0 to 2 pi. So this is how it looks on theirs. See, they bring the x down here and the y down there, and this is sort of what I think they call isometric. So it gives a better rendition here. Even though this is still climbing, it looks like it's going down a little bit, or not going much up at all, but it still is climbing here. It's just exaggerated the climb on the back side and minimizes the climb on the front side, but you're still heading out. And 0 somewhere is about 1.5, 3. Somewhere over here you're 4.5, and here you're 6. So really even hard to follow it on that one. As t increases, and yeah, you see they've got the arrow there giving the direction of increase. I forgot to do that on mine. Let's see, I still can. No. No. Yeah, I erased all that. Okay. Yeah. All right. Now, a real-life example, literally, of a helix is shown in this drawing, and this is, have y'all heard of Crick and Watson? Yeah, the double helix discovered how the structure of DNA worked. They knew it was cyclic and stuff, but no one could come up with quite how you can make these things tie in, and I can't remember, I remember reading about it, how they did it. It was just freaky. I think some third party made some comment, and they came back and said, hey, could we try that? Could we do it? And they started playing around with it and found out, yes, you can. You got two helixes going around, and then the I think these are the chromosomes or something here that connect to different locations. And there's a pattern too of which pairs with which, and as they go on up. So that's the double helix. Okay. Now, they skip to limits and continuity, skipping examples 3 and 4. I don't think they're quite as bad as that was, so let's try it here to do example 3. I may be totally wrong on it. Okay. It says represent the parabola y is equal to x squared plus 1 by a vector value function. Okay. Well, I guess we need to graph it first. Okay. And there will be 1 here. And then that's 1 and that's 2. That would be there. -1, 2 would be here. 2 would be 5, I think it is. -2 would be 5 as well. And then three would be 10. Okay, somewhere up about here and here. Okay, so here is approximately the parabola. Okay, now they drew an arrow in for you. I don't know why they chose to, but they did. It says try to represent that parabola by a vectored value function. Okay? Now, if you go back to when we first introduced parametric equations, find the variable that has the most complication in it. Okay? That would be the x here, right? Let that be your t. And then the y is really simple. What is your y? X squared, which in this case is t squared plus 1. Okay? Now when t is equal to 0, x is 0 and y is 1. So this is t is equal to 0. And when t is equal to 1, you're over here. And then your y would be 2. And that's exactly where you are there. So you're going in this way. This is t is equal to 2. Okay? this would be t is equal to 3. No, I'm sorry. 1 and 2. One and 2, okay, and then this would be t equal 3. This would then be t equal minus 1, because you're minus 1 on x and 2 on y. So this would be t is equal to minus 2 and t is equal to minus 3. So sure enough, you're going in that direction, increasing t. So your vector value function would be r of t would equal ti plus t squared plus 1 j. By that, x, y. Okay. Now that's one. That's not the only one, but that certainly would work. If you had chosen something else to be your t, you could have fiddled around with things like if you chose y to be the t, then x would equal t minus 1, the square root of t minus 1, or something like that. But who wants to do that? Okay, then you would be really limited in what values t you could take on. So,
Question.
yes.
On the t squared plus 1.
Mm-hmm. Right here or over there.
Okay, yes. We'll say it's like lower pair of x and y.
Yeah. Yeah. This is your x value. Let that be, because that's the most complicated thing in here, the x equal t. Okay. Then for any x equal t, y is going to be t squared plus 1 for every one of them. So then you take this x and put in for your x here, that would be ti plus t squared plus 1 j. T squared plus 1 parenthetical j. And that does it for you. And then all those values fit. I think if you had chosen x equal minus t here, then you would have had it going the other way. I haven't tested that yet, but I think that's what you give it. So the y is still going to be doing this, taking on the same values. Okay. Okay. Yeah, and they say the same thing. Had you chosen t, x equal minus t as a parameter, the curve would have oriented in the opposite direction and gone from right to left.
But why we want to take a t as a minus 1?
I can't imagine. It's just that you could have done that, and then you could have had the arrows going in the opposite direction, which is bizarre, but you could have done it if you wanted to. Okay, which I don't. Okay, so no, I'm just kidding. All right. So let's go and erase that one if it's okay. Yay. And let's see if we can squeeze in example 4. Sketch the space curve. I love this. C represented by the intersection of the, oh boy, semi-ellipsoid with the parabolic cylinder. Yay. Okay. I don't even want to sketch either one of those. Okay. So here is what we got. X squared over 12 plus y squared over 24 plus z squared over 4 is equal to 1. Now they call that, here's why they call it a semi-ellipsoid, because they throw this in. Z is greater than or equal to 0. Okay. I was going to say that's an ellipsoid. Why do they call it a semi-ellipsoid? Then I saw the second part. Z is always positive. Or negative, never negative, we'll say that. Now, let's just sketch that quickly. That's really not too bad, okay? I say, and then I start drawing poorly. I always draw poorly. Okay, let's try it again. Let that be my Z, that be my Y, that be my X. I wish I could do isometric better. I'd have trouble. Okay, that's not what I want to do. X, Y, and Z. Okay, and this one we do need our negatives back here, and over here, and down here. Okay. Now, you're coming in and out of the X by the square root of 12, which is 2 root 3. Well, root 3 is about something less than 2, and twice that would be something less than, so let's just say something a little more than 3. And then back 1, 2, 3. This is back a little more than 3. So this is where it intersects the x-axis on the xy plane. The y is going to be the square root of 24, which is 2 root 6. Now root 6 is something between 2 and 3. A bit closer to 2. And then you double that, and you got something close to 5 maybe? Let me think back on that again. I'm going to put it somewhere out there. 1, 2, 3, 4, 5, somewhere out there. Okay. So that's where it intersects that axis. Okay. And then your Z is going to be plus 2. All right. So there's your ellipse that's on the XY plane, and then these ellipses go like this, like this, like this, semi-ellipses. Okay, so you've got sort of a dome there, not too tall, long in the Y direction, and a little bit shorter in the X direction, or something kind of like that. Okay, now that we're going to intersect with the parabolic cylinder y is equal to x squared. Well, 0, 0 is going to be on that, so that's going to be right up here, because the cylinder goes up and down the z-axis. I mean, parallel to that. And then you have 1, 1, and minus 1, 1, something here. So this is on the xy plane, this is doing like this and like this. And then 2, 4, 1, 2, 3, 4. That would be somewhere out here. And 2, minus 2, 4, somewhere here. Maybe actually on that. I haven't checked to see, but it's coming like this and like that. So this is going down like this and down somewhat like this. It's a weird thing. It's going down the curve. Look in the book and you'll see a far better rendition than mine. It's not that funny. Okay, now it shows it going downhill pretty quickly there. Okay, one of those things it's going to look something like. Okay, let me erase some of them. Oops, that wasn't the one I wanted to erase. Okay. All right. Now, what that was y is equal to x squared, right? Now, it says sketch the space curve. somewhere in there I sort of have done it, believe it or not. I've sort of sketched that. Okay. But it's far easier to represent, well, I say far easier, because y is equal to x squared, you can then represent this as see, if you multiplied everything in that first equation by 24, you would have 2x squared plus y squared plus 6z squared is equal to 24. I don't know if that's helpful or not, but if y is equal to x squared, then you can say two x squared plus x to the fourth. But then you still have to, I was just playing around with that to see if there's something we could do, and I think not. I think let's go back and try the other thing. Let x equal t, so y is equal to t squared, and then from here you would get t squared over 12 plus t to the fourth over 24 minus 1 is equal to minus z squared over 4. Okay, and then multiply everything by 4. That would give you 3t squared plus, no, that's not right, t squared over 3. Duh. T squared over 3 plus t4 over 6 minus 1 is equal to minus z squared over 4. No, minus z squared. I'm just playing around here. Let's get rid of the minus sign, kinda, and make it 1 minus t squared over 3 minus t4 over 6 is equal to z squared. And then take a square root of that. And that's what your z would be. So z would equal either plus or minus, I think you have to do that, the square root of 1 minus t squared over 3 minus t4 over 6. I don't know, yeah, they do something like that. Then they work out common denominators and stuff like that, and you get something you can factor. And it's a real pain in the neck. But you see, let's carry it a little bit further. Z is equal to, now they only do the plus one. Oh yeah, because Z is always positive, so you don't need the minus sign. So it's the square root of 6 minus 2t squared minus t to the fourth over 6. Okay? So this will be, and that I think will factor, I hope it will because they factored it. No, I must have botched something up. There must be a 24 in here somewhere. I think that's supposed to be over 24, and I somehow lost that. Oh, of course. No? I don't know how I messed it up, but I did. If that was a 24, I think we're okay. But it's not a 24. So I guess they multiplied through everything by 24 to begin with. But anyway, we're out of time.
You just lost the 4 over the z squared.
Yeah, I blew it somewhere. I'm awfully close to what they've got, but not quite.
So if you had it, everything would be.
What's that?
If you had the 4 under the z squared at the very bottom, then.
Okay. Yeah, but where do you get the 4 to add it? This one that I took out here?
Yeah. Well. Yeah, I don't know.
Yeah, I don't know. I've just lost it. It's somewhere in there, but I've misplaced it. But anyway, we got something pretty close to what they did, but I didn't quite get it to come out. But anyway, that's how you get. It actually was, believe it or not, easier to get the parametric equations than it was to draw the graph, in my mind, even though I messed it up, but I messed up the graph too. We'll begin next time with limits and continuity. Be glad to get rid of those drawings. And not that we won't have to. So homework exercises, do some of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. Do 11 is at both Calc Chat and Calc View. 13 or 15, both are at Calc Chat. You can think about doing 17. It's should be at Calc Chat. I think you can do probably any of the odds 19 to 22, but 19 and 21 will be at Calc Chat. 23 through 29, they're all at Calc Chat. 25's at Calc View. 31 through 37, they're all at Calc Chat, and 31's at Calc View. 39 should be at Calc Chat. Let's stop there. I may have gone too far anyway. There's a lot of exercises here. But somewhere there, stop. If you feel like you can keep going, keep going. But we'll wrap those up next time. All right. Sorry I messed that last one up.